DC HiPot testing applies a constant direct current voltage to the equipment under test for a specified period, while AC HiPot testing applies a sinusoidal alternating current voltage to the equipment under test for a specified period. The industry standard uses a multiplier of 2 for direct current HiPot testing and a multiplier of 1.5 for alternating current HiPot testing. For example, an 11 kV cable would require a 22 kV direct current HiPot test and a 16.5 kV alternating current HiPot test. Direct current HiPot testing mainly identifies defects in the insulation, while alternating current HiPot testing additionally detects surface contamination and corona discharge. Alternating current HiPot testing creates capacitive reactance in long cables, which can limit the current flow at low voltages. Alternating current HiPot testing typically results in higher leakage currents than direct current HiPot testing due to capacitive charging. Direct current HiPot testing is more sensitive to insulation defects and suitable for testing equipment with high inductance. Alternating current HiPot testing simulates actual operating conditions and detects surface contamination and corona discharge. The failure of the 11 kV cable at 200 volts alternating current could be due to several factors. Firstly, the long cable length of 350 meters creates significant capacitance, which limits current flow at low alternating current voltages. Secondly, surface contamination on the cable insulation can lead to corona discharge and insulation breakdown. Thirdly, the two splices in the cable could introduce weak points in the insulation. Repeated HiPot testing can damage the insulation if done excessively or if the voltage is too high. It's recommended to limit testing to a few cycles and carefully monitor the leakage current. When performing direct current HiPot testing, the constant voltage stresses the insulation, revealing weaknesses like cracks or impurities that might not be apparent under alternating current conditions. This is because direct current voltage forces electrons to flow in one direction, concentrating the electrical stress at these imperfections. Conversely, alternating current HiPot testing subjects the insulation to a continuously changing electric field, which can better simulate the stresses encountered during normal operation. The alternating current voltage alternates the direction of electron flow, allowing it to detect issues like surface contamination or corona discharge that are influenced by the dielectric properties of the insulation. Capacitive reactance is a critical factor in alternating current HiPot testing, especially with long cables. Capacitive reactance impedes the flow of alternating current, particularly at lower frequencies and higher capacitances. A long cable, acting as a capacitor, stores electrical energy and opposes changes in voltage. This opposition to alternating current flow results in a limited current at low voltages during the HiPot test. The higher leakage currents observed during alternating current HiPot testing compared to direct current HiPot testing are primarily due to capacitive charging. As the alternating current voltage rises and falls, the cable's capacitance charges and discharges, creating a current flow that is superimposed on any resistive leakage current through the insulation. This capacitive charging current can mask small insulation defects, making it harder to pinpoint the exact location of a failure. Direct current HiPot testing is advantageous when dealing with equipment that has high inductance, such as transformers or motors. Inductance opposes changes in current, and applying an alternating current voltage to a highly inductive device can cause large voltage spikes due to the back electromotive force. Direct current HiPot testing avoids this issue by applying a steady voltage, preventing the generation of these voltage spikes. Alternating current HiPot testing is preferred when simulating actual operating conditions because it replicates the voltage waveform that equipment experiences in service. This allows for the detection of problems that are specific to alternating current operation, such as insulation breakdown due to dielectric heating or corona discharge caused by high-frequency components in the voltage waveform. The failure of the 11 kV cable at a low voltage of 200 volts alternating current with a 12 mA leakage current indicates a significant insulation problem. The high capacitance of the 350-meter cable limits the current flow at low voltages, but a leakage current of 12 mA suggests a substantial breakdown in the insulation. The capacitance of the cable can be estimated using the formula for capacitance of a coaxial cable, which is C equals 2 asterisk pi asterisk epsilon asterisk L slash ln d slash d, where epsilon is the permittivity of the insulation material, L is the length of the cable, d is the outer diameter of the outer conductor, and d is the inner diameter of the inner conductor. The total capacitive reactance can be calculated using Xc equals 1 slash 2 asterisk pi asterisk f asterisk c, where f is the frequency of the alternating current voltage. The impedance, Z, can then be found by using Ohm's law and the formula Z equals V slash I, where V is the voltage and I is the current. Surface contamination on the cable insulation can dramatically reduce its dielectric strength, leading to premature failure. Contaminants like moisture, dust, or chemicals can create conductive paths along the surface of the insulation, facilitating the flow of current and causing a breakdown. Corona discharge, a phenomenon where localized electrical stress causes ionization of the air surrounding the conductor, can further degrade the insulation over time. The two splices in the cable represent potential weak points because they introduce discontinuities in the insulation. Poorly made splices can have air gaps or voids that reduce the dielectric strength, making them more susceptible to breakdown under high voltage stress. The splices should be carefully inspected and tested to ensure they meet the required insulation standards. Repeated HiPot testing can be detrimental to the insulation if performed excessively or at voltages that are too high. Each HiPot test stresses the insulation, and repeated stress can weaken the material over time, leading to premature failure. It is recommended to limit the number of HiPot tests and carefully monitor the leakage current during each test. A sudden increase in leakage current indicates that the insulation is deteriorating and may be close to failure. To determine the appropriate HiPot testing parameters, it's essential to consult industry standards and manufacturer specifications. Standards such as IEE 400.4-2015, IEE Guide for Field Testing and Evaluation of the Installation of Shielded Power Cable Systems, provide guidelines for testing cables and other electrical equipment. These standards specify the recommended test voltages, durations, and acceptance criteria for HiPot testing. It is also crucial to consider the operating voltage of the equipment being tested. The HiPot test voltage should be high enough to stress the insulation, but not so high that it causes damage. A common practice is to use a multiplier of 1.5 for alternating current HiPot testing and 2 for direct current HiPot testing, as previously mentioned. However, this multiplier may need to be adjusted based on the specific characteristics of the equipment and the recommendations of the manufacturer. In the case of the 11 kV cable, the alternating current HiPot test voltage will be 1.5 times 11 kV, which equals 16.5 kV. The direct current HiPot test voltage will be 2 times 11 kV, which equals 22 kV. Before performing a HiPot test, it's essential to visually inspect the equipment for any signs of damage or contamination. Clean the insulation surface to remove any dirt or moisture that could affect the test results. Also, make sure that all connections are tight and that the equipment is properly grounded. During the HiPot test, carefully monitor the leakage current. A steady, low leakage current indicates that the insulation is in good condition. A sudden increase in leakage current or an erratic current flow suggests that the insulation is deteriorating and may be close to failure. If the leakage current exceeds a specified limit, the test should be stopped immediately to prevent further damage. After the HiPot test, allow the equipment to discharge completely before handling it. High voltage can be stored in the capacitance of the equipment, and touching the equipment before it is fully discharged can result in a severe electric shock. Use a grounding stick to ensure that the equipment is completely discharged before touching it. In summary, HiPot testing is an essential tool for evaluating the integrity of insulation in electrical equipment. Direct current HiPot testing is best for detecting insulation defects and testing equipment with high inductance, while alternating current HiPot testing simulates actual operating conditions and detects surface contamination and corona discharge. The choice between direct current and alternating current HiPot testing depends on the specific application and the type of equipment being tested. The LON cable failed at a very low voltage with a relatively high leakage current, indicating either contamination or weak points in the cable insulation or connections. Because of the length of the cable and the two connections, alternating current HiPot is the recommended method to simulate the load that it will face and to see where the contamination or weak points in the cable are. But it is also important to make sure that the cable has fully discharged before handling it and that the cable has been cleaned to prevent further contamination. Remember that safety precautions should be followed and that the voltage being tested should be appropriate for the load. If there is suspicion of damage to the insulation, then the voltage should not be tested as high because it might further damage the system. In that case, it is best to start with a lower voltage to prevent damage to the cable.